So when finding the area, well, we did it by finding areas of triangles. But look at these areas being left out, and look at these areas going out of the rectangles outside of the function, or outside of the area that we want to find. Well, the idea was to then find the area of having more rectangles, maybe 100, maybe 1,000,000, but then we found out that having infinitely many of those rectangles would give us the actual area under the curve. But of course we didn't find the area of infinitely many rectangles. I mean, we used in this case a Riemann sum, and we found the limit as n approaches infinity. That's how we define the integral back in Calculus 1. So in Calc 2 we're going to use the same idea. Well, we already did the description of this, of how we're going to find the arc length. So in this case, so instead of finding the area of an arbitrary rectangle, we're finding the length of an arbitrary arc length in this case, and that's going to be based on the Pythagorean theorem. So we're going to use this formula to get to the arc length. Well, so we need to, what we want to obtain is, well, I don't have the formula here, we'll derive it actually. So we need to somehow have a, oh, actually we have it here, never mind. Oh no, I don't have it. Well, let me write down the formula that we're supposed to obtain. So L equals the integral from a to b of the square root of 1 plus f prime quantity squared with respect to x. Alright, so we have to obtain that formula. Well, if you observe that formula, that's the square root of something squared plus something squared. That looks like the Pythagorean theorem, so to speak. But now, the thing is, how are we going to go from this expression that we set up yesterday to this? Well, let's do one thing at a time. So somehow we have to obtain an f prime quantity squared, but in this case we have delta x and delta y. How can I get an f prime from there? Well, so apparently there doesn't seem to be any algebraic trick to get this done. Now, so we are going to factor the quantity inside of the radical, but wait a minute, how can I factor that? How could we factor in a way that we can get this result? Number one, for example, okay, let me go back to basic algebra real quick. So whenever we had the polynomial, I don't know, x cubed plus 3x squared, okay, how can we factor this polynomial? Any ideas? Factor in x squared, that is the greatest common factor, right? And x plus 3. Good. What about this one? Can we factor anything out of this one? No? You say no. Anybody else? Yes? No? Well, so at first glance, it doesn't seem like we can factor anything out, and I agree, because well, we don't have any excess on the second term. However, we can still factor an x. I'm going to factor an x squared, and this will be 1 plus 1 over x squared. I mean, if we go back and distribute this, we should get back to the x squared plus 1. So we're going to use this algebraic mischief right here to come up with a formula for the arc length. In this case, what are we going to do? Number one, so let me continue here. So L sub I is the square root. I'm going to factor out delta x sub I squared. So delta x sub I is quantity squared. That's going to leave us with 1 plus 1, or rather plus delta y sub I squared over delta x sub I squared. Do you see this delta y over delta x? Somehow that's going to take us to later dy dx, which ultimately will be our f prime. Alright? Now let's do one thing at a time. Number one, how about we write this quotient of squares as a square of the quotient, and at the same time I'm going to use the product rule for radicals. So that's going to be 1 plus delta y sub I over delta x sub I quantity squared equals to L sub I. Well, the square root of something squared, it's simply the quantity inside of the radical, and that's 1 plus 1 plus delta y sub I over delta x sub I quantity squared. Well, to make this look more closer to make it look closer than what we want to obtain, I'm going to write this delta x after the radical, so we can see the resemblance of what we want to obtain. So this is the radical expression 1 plus f prime dx, isn't it? Which is from the formula there. However, this in terms of delta x, it's just for a finite element, for that element that we sample from those infinitely many to describe the expression here, to describe the derivation. However, this is not yet the formula for the arc length between A and B. This is just a formula for the arc length of only one element in the partition. We need to find this all of this by adding infinitely many of those. So in this case, let's add infinitely many of this length, and we do that by finding, so it's not going to be any more, so number one, that'll be L equals L sub 1 plus L sub 2 plus L sub 3 plus dot 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 plus L sub n minus 1, or L sub I rather, L sub I minus 1 plus, actually let me use L sub n and L sub n. Of course I'm not going to write one expression for each. It would correspond to, for example, delta y 1 delta x 1 times delta x1, but I'm not going to write this. Instead, I'm just going to represent this as an infinite sum. Alright, so in this case, this will be the sum from I equals to 1 to n of the square root of 1 plus delta y over delta x. Alright, well that's first, this is first approximately, by the way, and so we want the exact, not the approximation, by, in this case, finding the limit of the sum from I equals to 1 to n, 1 plus delta y, I forgot the square, and as n approaches infinity, and this will become the integral from a to b of the square root of 1 plus f prime squared dx. So again, in a similar way that we obtain the area under the curve, but now we're not multiplying length times width. In this case, we are using the Pythagorean theorem to find the hypotenuse that represents that partition of an arc length, and well, ultimately adding this symbol which means sum, infinitely many of them, that's actually going to lead to the integral in this case. So how about we look at an example of how to find the arc length. And by the way, guys, these exercises are going to require a lot of algebra, a lot of techniques here and there. Well, I'm going to go over every single detail, so let's see. Find the arc length, the length of the arc for the curve f of x equals x to the 3/2 between x equals to 0 and x equals to 4. All right, so let's see. So number one, L, which is the arc length, that's the integral from a to b of 1 plus f prime squared with respect to x. Well, what do we need to do in this case? So we need the derivative of the function. So the formula to find the arc length calls for the derivative of the given function. So let's go ahead and do that. So finding the derivative of f of x equals 3/2, well, that's prime 3/2 x to the 1/2, which is 3/2 square root of x. And it would be convenient to write it in radical form because, well, you'll see why. So let's integrate from 0 to 4 the square root of 1 plus what's this? 3/2 root of x, quantity squared with respect to x. So a couple of things are going to happen here. Number one, this square is going to affect both the numerator and the denominator of the coefficient. So that's going to become, okay, let me write it down. The integral from 0 to 4 square root of 1 plus 9 over 4. And also, so it affects that way, but also cancels the radical, because square root and the radical are inverse operations, and that's just x with respect to x. And this is the integral that we have to compute in this case to find the arc length of this function between 0 and 4. Well, so we need to decide what method to go about this integral. Any ideas on what method to go about? What method would be good? Anyone? Trig substitution, maybe because of the radical, right? However, we don't have a square here. If we had a square, we would have done trigonometric substitution. However, well, this is degree 1. The derivative of this would be degree 0. We have outside a degree 0, so we can use simply u substitution. So let's go ahead and do the u substitution. So u equals to 1 plus 9 over 4 x du equals 9 over 4 dx, and dx equals to 4 over 9 du. Alright, so what I'm going to do next, well, maybe you're used to do it, maybe not. However, I strongly suggest that you do it this way so you don't have to write a lot of symbols when back substituting. In fact, this will save the back substituting part of the problem. And what I'm going to do is change the limit, which is technically the correct thing to do, because when we are evaluating a definite integral, notice we're doing a u substitution to send the problem to the world of u, which is an easier world to solve the problem. But we also have to carry the limit to the world of u with their corresponding values. Well, how are we going to do that? So we're going to evaluate u at 0 and u at 1. So u at 0, at 4, not at 0, not at 1, So plug in 1 plus a 9 over 4 times 0, well, that's going to be 1. And 1 plus a 9 over 4 times 4, cancel the 4s, that equals to 10. Alright, so let's change the integral using the substitution. So well, let's write down the integral with the new limit of integration. So that's the integral from 1 to 10 times the square root of u, and dx becomes 4 over 9 du. Okay, so let's do a couple of things. Number one, I'm going to take that 4 over 9 out of the integral. U to the 1/2 du, and that's because we cannot integrate the radical just the way it is. So this will be 4 over 9 u to the 3/2 over 3/2 evaluated from 1 to 10. So one thing at a time. Number one, dividing by 3/2 is the same as multiplying by 2/3. And let me leave this as u to the 3/2. I'm going to deal with that later. So 2/3 times 4 over 9 u to the 3/2 evaluated from 1 to 10. So, well, 2 times 4, that's 8, and 3 times 9 is 27, so that's 8 over 27. That's not going to reduce anything. U to the 3/2 evaluated from 1 to 10. So we may now go about the fundamental theorem of calculus. Again, check this out. Notice I changed the limits to the corresponding values in the world of u. This way we don't have to go back to do the to do the back substitution and write a lot of terms. Instead, we can just go back and substitute for u in this case. So that's going to be 10 to the 3/2 minus 1 to the 3/2. And we need to reduce radicals to exact form and to the simplest form in this case. So let's see. So, well, 1 to whatever power, it's still going to be 1. All right? But in this case, how do we go about? Well, that's 8 over 27. That's going to be the square root of 10 cubed minus 1. How do we simplify the 10? The square root of 10 cubed? Well, you don't want to take 10 and raise it to the 3rd power. That's going to give us a big number, and it may be hard to find the square root. Instead, use properties of radicals. So, whenever we have a to the m over n, that's the nth root of a to the m, or the nth root of a, the whole thing to the nth power. So we may use one or the other. You will see me using one or the other depending on the complexity or the nature of the number that we want to simplify. If we have like a perfect square, we may use the latter one. But in this case, the number 10 is not a perfect square, so we're going to work with 10 to the 3rd power. So to simplify this radical inside of the parentheses, we're going to go 8 over 27. Well, so I'm going to break up this 10 cubed as 10 squared times 10. That's going to take us back to 10 cubed. And then minus 1. And in this case, well, let me highlight the perfect square. So let's find the square root of the perfect square. That's going to go outside of the integral as a 10. So 8 over 27 times 10 root of 10 minus 1, which is final answer. Alright. And it's important to reduce all these radicals this way, because if you put these answers without simplifying them on WebAssign, it may not take them. So it might be asking for simplified versions. Alright. Let's do another one. Alright. The next one is the one that really requires a lot more algebra. So, let's find the length of the arc for the curve y equals x cubed over 6 plus 1 over 2x between 1 and 2. Alright, number one, we need to find the derivative of this function, but we cannot differentiate this function the way it is. Number one, that's because we have an x in the denominator, so we'd better write the function this way. Y equals to 1 over 6 x cubed plus 1 over 2 x to the negative 1. Only then we would be able to differentiate this. Alright, so let's see, the derivative y prime will be 3 over 6 x squared, and negative times a positive is negative 1/2 x to the negative 2. Okay, number one, the coefficients on the first term reduced to 1/2 x squared, and the x to the negative 2, I'm going to write it in the denominator with positive exponent. Okay? So let's go to the arc length formula. So the integral from a to b of the square root of 1 plus f prime quantity squared with respect x. So, well, that's the integral from a to b, that's from 1 to 2, of the square root of 1 plus that madness here, this derivative right here, which in this case is 1 over 2. Let me write it actually as x squared over 2 instead of 1/2 minus 1 over 2x squared, quantity squared. Whoa, that's going to be interesting. So we're going to do a few things at a time. So yes, we have a binomial and we have to square the binomial. However, notice that binomial that we have inside of the parentheses that at the same time is inside of this radical. Notice it has x everywhere. They're all over the place. So my advice, when you run into this, when you run into something like this, write this quantity as a single rational expression. So this is what I'm going to do. I should have made some space over here. Whoops. So I'm making some space in order to combine like terms by finding the LCD. In this case, well, we already have the 2's. We need to multiply numerator and denominator by x squared. So only then we should be able to put them together. So this will be the integral from 1 to 2 of the square root of 1 plus x times x squared times x squared. That's going to give us x squared minus 1, I mean x to the 4th, not x squared, x to the 4th minus 1 over 2x squared, the whole quantity squared. Alright, let's do one thing at a time. So in this case we have a quotient being squared. What we're going to do here is, well, number 1, the integral from 1 to 2, the square root of 1. I'm going to leave some space over here for another LCD. Plus, not that much space. Okay, I'm going to square x to the 4th power minus 1, but I'm not going to FOIL the binomial yet. And 2x squared, quantity squared, that's going to give us 4x to the 4th power. Okay? Well, so again, this number 1 can be expressed as 1 over 1, and we will be able to combine the fractions together in a similar way that we did before inside of the parentheses, but this time we're going to do it for the whole radicand. So let's multiply numerator and denominator by 4x to the 4th, and only then we will be able to have everything together as a single fraction. If you want to FOIL the binomial in your head at the same time, that's fine. But however, I'm going to write all steps. So we're going to get 4x to the 4th plus x to the 4th minus 1 quantity squared divided by 4x to the 4th power. Alright. That with respect to x. So we should be able to work with the numerator of the radicand. Again, there's a couple of ways to express this or to expand this binomial. Number 1, by FOILing, but that takes some time. I'm going to do the squaring the binomial, which I have done a few times before. So squaring the binomial, let me recall the formula: a plus or minus b quantity squared. That's the same as a squared plus or minus 2ab. Depending on the case, it could be plus or it could be minus, plus b squared. Okay, so in this case, I'm going to square the first term. Okay, number 1. From 1 to 2. So that's the integral from 1 to 2, square root of 4 x to the 4th plus, okay, x to the 4th squared, that's x to the 8th, and in this case minus 2 times x to the 8th times 1. Well, we don't need to write that one, alright? And plus negative 1 squared, well, that's 1. Let's combine terms here. Well, actually it's 2 times x to the 4th power. My bad. So the whole thing divided by 4x to the 4th power. Let's combine like terms in the numerator of this radicand, and notice that as like terms we have this x to the 4ths, x to the 4ths. Let's combine them from 1 to 2. So that's going to be 4x to the 4th minus 2x to the 4th. That's going to give us, well, x to the 8th in the first place, the highest power first, plus 2x to the 4th plus 1. Whole thing divided by 4x to the 4th power. Can we simplify this further? Of course. Did you notice the form here? The trinomial that we have in the numerator? Do you see the pattern? Square and, well, 1 degree, well, half of the degree less, and the 2 times, you know. Well, let me do some examples on the side. For example, whenever we had like something like x plus 3 squared, that's x squared plus 2 times this, that's a 6x plus 9. And now in the backwards direction, what if we had x squared, how can I write this? Okay, x squared plus 14x plus 49. So let's do the backwards. What would this be equal to? X plus 7. Okay, do you see this pattern here? So basically what do we have? A squared plus 2ab plus b squared. Don't we have this a squared plus 2ab plus b squared? Okay, so this is the reason I'm stopping here and going back to looking at perfect square trinomials. It's because the minute we see an 8-degree polynomial, first thing we're going to do is freak out, right? But however, well, this one can still be expressed as a binomial square because it follows the pattern a squared plus 2ab plus b squared. So in this case, I'm going to factor this. Oh, actually, let me do the simpler one. X squared plus 2x plus 1, that's x plus 1 squared. If you square this binomial, you should get that. This is equivalent, but we have the powers actually multiplied by 4. Should follow the same pattern. So this will be then the integral from 1 to 2. That's the square root of x to the 4th plus 1, quantity squared, divided by 4x to the 4th with respect to x. So we should be able to simplify this madness finally, because we may use the quotient rule for radicals in the first place. That's going to be the integral from 1 to 2, the square root of x to the 4th plus 1 squared, divided by the square root of 4x to the 4th. And the nice thing about this is that both numerator and denominator are perfect squares, and you'll see how this will simplify really, really nicely, despite all these, all these crazy algebraic steps we did. Well, on the one hand, we can cancel the radical with the square, and over here we will divide 4 over 2 to have an x squared and the square root of 4, which is 2. So this is the integral from 1 to 2, x to the 4th plus 1 over 2x squared dx. And what are we going to get here? So this is what we're going to do here. We can split this fraction as the integral from 1 to 2 of x to the 4th over 2x squared plus 1 over 2x squared with respect to x. Let's simplify each term. X to the 4 over x squared, that's going to be the integral from 1 to 2 of x squared over 2. And you know what, instead I'm going to change notation to 1/2. I think it would be easier to integrate it, and that's just going to be x to the second power in the denominator. I'm going to move it to the numerator or rather as x minus 2, and we should be able to integrate this. Now see how nice this is to integrate. So don't even attempt to integrate this madness right here, because check this out. Just try to take the derivative of this to do the u substitution. Good luck with that, right? You will have like a crazy chain rule along with a quotient rule, and then in fact, I forgot the dx. We don't have anything multiplying the dx, so we could potentially work as the u du setup, do we? So this is not how things are going to work in arc like this time. So we need to do a bunch of algebra. Basically expanding polynomials or binomials and identifying perfect square binomials backwards to factor them as binomial squares. So that's what we did. We went back and forth between those two. So we're ready to integrate this. So that's the integral. That's 1/2 x cubed over 3 plus 1/2 x to the -1 over -1, evaluated from 1 to 2. A lot of factors, a lot of negatives. Let's simplify that and write it nicely. So 1/2 times 3 in the denominator, that should be a 1/6 x cubed, and plus a negative number, that should be a negative 1 over 2x. I'm going to have this x to the -1 as x to the first power in the denominator by laws of exponents. And that from 1 to 6. Oh wait, no, not to 6, it's to 2, right? Alright. So let's see. F of b minus f of a. You know, we've done this a lot of times. So that's a 1/6. That's 1/6 times 2 cubed minus 1 over 2 times 2 minus 1/6 times 1 cubed minus 1 over 2 times 1. Those are the upper limit and lower limit respectively. Alright? Okay, so what's this going to be? 2 cubed, which is 8, times a 6th. That's 8 over 6 minus 1/4. And then minus, that's 1/6. And minus, careful, because that's a plus 1/2. Alright? Let's combine this number to get these numbers together. How about we combine 6th with 6th, and this is basically 4ths with 4ths, okay? So 8 over 6 minus 1 over 6, isn't that 7 over 6? And 1/2, take away 1/4. That's going to be 1/4. Alright, so let's combine these fractions together by finding a least common denominator. So we need 6 over 6 and 4 over 4. So 7 times 4, which is 28, plus 1 times 6, which is 6, over 24. That's a 28 plus 6, which is 34 over 24. And this reduces nicely to 17 over 12, which is final answer.